Okay, so in this video, we're going to look at conducting two sample hypothesis tests. So we're going to start with two sample proportions tests, and we're going to be able to use the same proportions test that we used in the last video when we did one sample proportions. So this is the crop test. Now, for this example, we have a car manufacturer who wants to improve the quality of products by reducing the defects and also increase the customer satisfaction. He monitors efficiency of two assembly lines on the shop floor. On line A, there are 18 defects out of 200 samples, while in line B, he found 25 defects out of 600 cars. At 5% significance level, is there a difference between the two assembly procedures? Now, because this is a two sample test, we're not just going to have a single value for X, we're going to have a vector for both X and N. And so we can enter this as X equals C, and then list our two successes, the defect numbers from each assembly line, and then our sample size also will be a vector. We'll have 200 to go with 18 and 600 to go with 25. We will specify the alternative. We want to know if they're equal, or different. So we'll use two-sided. And we're going to run this. And our outcome here, again, we're looking ideally for the p-value. Our p-value is less than our significance level, so we can reject the null hypothesis that the two proportions are equal. And this is sufficient evidence to indicate that the two proportions are unequal. And then we have our confidence interval here, which is the confidence interval for the difference of the two proportions. And then we also have the sample estimates of the two problems, proportion 1 and proportion 2, provided for us in case we need them. The center of our confidence interval would be the difference between these two values. All right, so that was much easier than calculating things by hand. Now, again, we can, in theory, do a z-test for very large samples that are normally distributed, where we know the population standard deviation, but this is so rare that it's almost never covered in textbooks. And so instead, we're going to simply move on to our t-test example. Now, in this example, we have a population of 10 students. They were given the same test at the beginning and end of the school year, and we would like to use a paired t-test to determine if the average score of the second test has improved over the score of the first test. Now, to do a paired t-test like this, we need to first enter the data that's provided. So the scores from the first test in order of students. So they don't have to be in any particular order, but they do have to be in the corresponding order for a paired test. And so this is the data that was provided for test 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and make sure I don't have any typos because that is a thing that can happen. All right, that looks good. And then X2. One, 2, 3, 4, 5, 6, 7, 8, 9. I missed a value. This is why we check 89, 92. There's an 82 right there. 86, 91, 88, 95, 100. All right, X2. Okay, so once we have our two values, The null hypothesis is that the two means are equal, or that the difference between them is actually zero. And then the alternative is that the difference between them is not zero. Now, there's a couple different ways that we can run this test. So fundamentally, we're turning this into a one sample test. So we can use the t-test function that we did before, and we can say x1 minus x2. If there's an improvement, this difference will be positive. We can say mu, the null hypothesis, the difference is zero, and then the alternative is greater. And again, I want to stress that in this example, it's important what order you do the subtraction in. If you want to do x1 minus x2, then you would need to do less for the tail, because you would expect that the first score would be lower than the second score, and so you'll get a negative value. Now, our results of our test, our p-value is extremely low, so we would reject the null hypothesis. There is a difference, and we can see here our calculated confidence interval for the difference of essentially the improvement of the training on the second test. Now, we can also actually just use the same test without subtracting. T-test, oops, not down there. T.test, we can do x2, x1, and the order that you enter these in matters when you do this in this way. Alternative, all this much is the same, but then you can specify paired equals true, and it will do the subtraction for you. But again, the order that you enter the values in, x1 or x2, is going to matter. If you enter them as in x1 and then x2, again, that would mean that you want the difference to be lower than zero because you want x2 to be bigger, and then you would have to do less for that tail. But paired equals true will avoid having to do the subtraction. And then if you run that, again, you get the same p-value, you get the same confidence level, and it just calculated those differences for you rather than you having to do the subtraction yourself. But the results are exactly the same, and it's completely equivalent. Now, if we want to do this from existing data, we can also do that. And so I'm going to load a data set in for this example. So data set 7, import. And we're going to change this. We'll call it data 1. And we'll just call it data. And we're going to run this. Now we're going to load in a package that we used in a previous video. Again, if you haven't used it before, you will need to use the tools to first install it. And then we are going to filter the data. Data 1 is going to have our data set, but we're just going to use gender equal to 1. And data 0 is going to come from the same data set, but gender will be equal to 0. So I have variables in this data set. If I want to look at it, where I have a gender and a salary value. And so I'm simply filtering my data so that it includes only the first gender information and the second gender information so that I can compare the two genders and their salary. Now, once I have these separated like this, then I can also do a t-test on the result. So data 1, and the annual salary has a space in it, so we use these backslash, back tabs, whatever we call them, in order to surround our variable name. And then data 0, same thing. Now, this var.equal function is essentially asking us, are we doing pooled or unpooled? If we do pooled, then we would specify var equal to be true, because pooled t-tests assume that the variance is equal. And here we're assuming the variance is unequal, and so that's an unpooled version of the test. And then our alternative, if I can spell, is two-sided. Because we just want to know if they're different, not that one is larger than the other. I don't remember at this moment whether gender 1 is men or a male or female. So all I want to see is if they're different. And if we run that, we can see the results. And again, we get a p-value that's very low, lower than basically any alternative significance level that you might want. The mean of X and the mean of Y of our two different data sets. And we also have a confidence interval that indicates that the mean difference of the data set is somewhere between 21,000 and 4,000. The sign of the difference is just a matter of which variable column is larger than the other one. And again, normally it will do the first one minus the second one when you enter it in this order. And so this is suggesting that in fact gender 0, whatever that is actually larger than gender 1 because it did the subtraction in that order. So those are our main two sample t-tests. Again, variations on the t-test. Again, you can change this to true to be pooled if you want it to be pooled. Again, that's a strong assumption that the variances are equal. If that is in fact the case, you should test to see if that's true. So there is a variance test that we're not going to talk about it right now. But you can also just make box plots to see, at least visually, whether or not that seems reasonable or not. But it is safer and to not make that assumption. And so variance equal false is a better thing. If you don't have good reason to think the variances are equal, you should do the unpooled test and set the variance equal to false.